Welcome to the first part of our 21st lecture in our Probability and Statistics course. Today we are going to talk about confidence intervals where the variance of the population is unknown ahead of time. And this is the more realistic situation. All of our work involving confidence intervals is finding confidence intervals for population mean. As I said before, that is not the only type of confidence interval. You can find confidence intervals for other population parameters. But we're just focused on finding confidence intervals for population mean, which is probably the most basic and the most important type of confidence interval that exists. So when we're talking about confidence intervals, we are trying to find a way to estimate the mean of a population. At the point that you're asking questions about the mean of the population, you likely do not already know the variance. It is unreasonable to think that one would know the variance to have a precise numerical value for variance when you're just attempting to estimate the mean. So we did make that assumption to simplify things a bit, but it is not actually realistic. How we're going to move past this is that we are going to use sample variance as an approximation to population variance when our sample size is large enough. So we have been operating using an expression of this type to derive our confidence intervals. And according to the central limit theorem, an expression of this type will be approximately a standard normal as long as you have finite variance and n greater than 30. Finite variance in your population and little n greater than 30 in your sample. So more than 30 observations in your sample. So we are interested in expressions of this type because of the central limit theorem. We're going to replace it with an expression of this type, where population standard deviation has been replaced with sample standard deviation. And it's not just a great approximation for relatively small values of sample size, but if sample size is large enough, then it becomes a good approximation, and you can proceed as if this expression were a standard normal. The bulk of the work will be done by this theorem, so confidence intervals for mu, population mean, when the variance is unknown. If we have a population, sigma squared is known to be finite so that the central limit theorem applies, but is unknown, and we'll say more about that in a moment, and your sample size is greater than 40 here. So we required a sample size greater than 30 for the central limit theorem to apply. Here we're requiring that sample size be a third again as much larger as it needed to be to just have the CLT apply. So we're adding 10 to 30 to get 40. So we're increasing by 133% here, the size of the sample that is needed. This idea that you could know that variance is finite without actually knowing what it is, that does seem outlandish to some folks. Like if you knew that it was, how would you know that it was finite without actually knowing what it is? But it's entirely possible. For instance, we're going to look at an example shortly where we're flipping a coin and we don't know the probability of heads for a single flip. We know that that is a Bernoulli random variable, and we don't know what p is, the probability of seeing a heads in a single flip, but we know that it's a number between 0 and 1, and we know that the variance is going to be p times 1 minus p. So we know that variance in that case has to be finite because we know our population is Bernoulli, and Bernoullis all have finite variance. We don't know what the variance is, but we do know that it's finite based on what we know about the population. So it is not actually unreasonable. There are lots of situations where you know that variance has to be finite, but you don't actually have a numerical value for it. Alright, given these three conditions, then the 100 times 1 minus alpha % confidence interval for population mean is going to be given by this expression. This looks exactly like the formula for confidence intervals that we had in the previous lecture, except sigma has been replaced by s. And again, I remind you here that s is the square root of s squared, which is to say it's the square root of sample variance, giving us s equal to sample standard deviation. And as another quick reminder here, we have our formula for sample variance. So sample variance is computed this way. This was not the definition of sample variance, this was rather a theorem that gave us a nice way to compute sample variance. So you can find this expression based on the observations that you make, your n observations for a sample of size n, and you can take the square root of that to find sample standard deviation. So let's have an example. Suppose you flip a coin, and I wrote fair coin out of muscle memory, but it is not a fair coin in fact, or it's certainly not known to be fair. We're about to try to estimate the likelihood of seeing a heads. So suppose you flip some coin that you don't know much about 41 times and you see 33 heads in those 41 flips. That seems like an unreasonably high number of heads if you did think it was a fair coin, so maybe it's not fair. We are going to construct a 95% confidence interval for the probability of seeing a heads in a single flip. And I also want a careful interpretation of the confidence interval that we find. So don't just give me an interval, also explain what it means, how you think about it, and what the significance of this interval is. Alright, so we do have a population of Bernoulli random variables here. We have our coin, we could flip it from now until the end of time, and that would give us a countably infinite collection of IID Bernoulli random variables, each having unknown parameter p. P is the population mean mu, so mu is p here, and it is unknown. P is going to be the probability of seeing a head in a single flip. That's the parameter that we want to construct a confidence interval for. We also know that population variance, sigma squared, will be p times 1 minus p. We don't know what that is. It is also unknown, but we do know that it's finite, as I mentioned in my little thought bubble above here. So because p is a number between 0 and 1, p times 1 minus p will also be a number between 0 and 1, and is definitely finite, even though it is unknown. So since we are attempting to construct a confidence interval and variance is unknown, the theorem that was just stated will be the appropriate theorem that allows us to do this. So we're going to use S, sample standard deviation, in place of population standard deviation in our confidence interval. And this is a typo. I should be saying n is greater than 40 here. N is actually equal to 41. We need n to be greater than 40 to make use of this theorem, and it is greater than 40, being 41. We sort of flipped this coin the minimum number of times that would allow for this procedure to be acceptable, for which this procedure would be acceptable. So n is actually equal to 41, which is greater than 40, is what I mean to say there. So make note that because this is a Bernoulli, each of our random variables is either a 0 or 1. So I'm adding up a bunch of zeros and ones when I take the sum of my observations. My xi, I going from 1 to 41, is a collection of zeros and ones that I sum, and there are 33 ones, and the remaining, I suppose, 8 random variables are zeros. So when I add those up, I get 33. We've used this trick before when dealing with Bernoulli random variables, when thinking about coin flips in particular. But the sum of the observations gives you the number of heads that were observed for a sample taken from such a Bernoulli population. So since there were 33 heads, the sum of these xi are 33. One more time, the key to this is the fact that each of them is 0 or 1, 0 for tails and 1 for heads. If this has given you any trouble at all, then please write out some simple examples. So write out what you might see explicitly in 7 coin flips, a bunch of zeros and ones, add them up, and see that that sum is the number of heads. Likewise, if I sum the squares of those Bernoullis, I also get 33. That's because 1 squared is still going to be 1, and 0 squared is still going to be 0. So summing the squares of the Bernoullis is exactly the same as summing the Bernoullis themselves. Nothing has changed there. These two observations allow me to calculate sample standard deviation. Well, rather, sample variance first, which then gives me sample standard deviation. So my formula for sample variance is shown here with n equal to 41 in place. The sum of these squares is 33, as we mentioned, and the sum of the variables themselves is also 33. I can solve this arithmetically, and I get about 0.16, meaning its square root is going to be about 0.4 here. So one point to make at this juncture is that this course should really probably have a software component to it. The math department is hesitant to do that because that makes it closer to a programming class, but all working statisticians are going to be using software to do calculations, be it R, an excellent free program, it's just the capital letter R if you'd like to search for it and learn a bit about it, or SAS, again, 3 capital letters, SAS, or even a spreadsheet like Excel will let you do a fair amount, or the free ones like in the LibreOffice or OpenOffice suite. So this example is handpicked because we don't have to add up 40 or more than 40 different numbers. Instead, because it's Bernoulli's, we have these simple truths like the sum of the squares just is the number of heads that you've seen. Really, examples that I would like to give you, and I am going to give you a sample problem in a moment where I just have to hand you the sample mean and the sample variance, because I'm not going to give you a list of 50 numbers and make you calculate the sample variance of those numbers without us having a software aspect to the course. So that's unfortunate. I apologize for that. More advanced statistics classes will always use software, and that's really the way that these kinds of things are done in the modern world. So I was pleased with myself to have found this example that we could do explicitly without having access to something like R or even a spreadsheet, but it is somewhat unfortunate. All right, so we have found the sample standard deviation. It is a simple matter to find the sample mean for our 33 heads and 41 coin flips, and now we can write down our 95% confidence interval. Note that I have my 1.96 in here, that is the z-value associated with a 95% confidence interval. I've got my sample mean, my z-value, my sample standard deviation, and the square root of the sample size. And I get 0.68 to 0.92 is my 95% confidence interval for the probability of seeing a head in a single flip of this coin. I do not think it's a fair coin, likely. According to this confidence interval, 0.5 is not in the interval. So according to these calculations, it doesn't seem terribly likely that this is a fair coin, which fits with our intuition of seeing 33 heads and 41 coin flips. That doesn't seem like it's likely 50-50. How do we interpret this carefully? So, we have a 95% level of confidence that P, the probability of seeing a head in a single flip, that was our population mean. We have a 95% level of confidence that P is in the interval from 0.68 to 0.92. What I mean by that is, we don't actually know whether or not P is in that interval. I can't say there's a 95% chance that P is in that interval, because it either is or is not. Neither P nor this interval are random. We don't know if P really is in this interval, but we do know that the procedure that we use to generate this interval, it successfully generates intervals which contain P 95% of the time. So the procedure that we use to generate this interval, it gets it right. It generates intervals which contain population mean 95% of the time. We don't know if it got it right with this interval or not, but we have a 95% level of confidence in the interval, given that the procedure used to generate it is 95% trustworthy in some sense. It could be that this interval is one of the 5% of the cases. We don't know, but we have a 95% level of confidence in this interval in the sense given here. All right, questions about this. It is a subtle point. I always have students arguing with me that they should be able to say that there's a 95% chance that P is in that interval. You really cannot. And if it is not clear to you why, please talk to me about it. You can go back and look at part 2 of the last lecture. One of my favorite metaphors is the one where we talked about here we have a random interval and a fixed point, population mean, and think about that versus if you have a fixed interval and a random point, right? I can say that there's a 95% chance that Z shows up in the interval from negative 1.96 to 1.96, but once I observe Z to be, say, 2.4, I can no longer say that there's a 95% chance that 2.4 is in the interval from negative 1.96 to 1.96. That's gibberish. It's just not in there. There's nothing random about that question. So that was the second interpretation that we gave of confidence intervals in part 2 of the last lecture. Do have a look back at that if you are still having some issues with this, and I'd be happy to talk to you about it in office hours or in a one-on-one meeting via our BCU room. Word to the wise, lots of our test questions going forward are going to be about interpretation. So it is in your interest to make sure that you have a handle on interpreting these ideas in a accurate way. All right, let's have you do a sample problem. So you work for a manufacturer and you folks make some steel I-beams. Your target allowable uniform load, we're going to call this the target capacity or load capacity, is 10,000 pounds, let's say. You know the load capacity of each individual beam that is made. It's going to vary a bit from beam to beam just because of inconsistencies in the material or in the manufacturing process, but you know the load capacity of the beams that you manufacture to be normally distributed. You don't necessarily know the parameters, but you know it is normal, and that's not an unreasonable assumption if you look deeper into normal random variables. So suppose you're part of quality control. You're going to go out and get 101 of these beams that your company has made, and you are going to test the load capacity of each of them. You find the sample mean for this sample of size 101 to be 9,874 pounds, and you find the sample variance to be 10,712. That would actually be pounds squared, would be the units, if you're interested in that. But you find these numerical values for sample mean and sample variance. And again, this is a point where really you would get a list of 101 numbers, and you would have to calculate sample mean and calculate sample variance. But I'm not going to make you do that by hand, so I'm just saying that suppose you had such a list of 101 numbers, each number was the load capacity of a beam in your sample, and you were able to calculate the sample mean and the sample variance using the formulas that we have outlined in the course, but likely using the help of a computer as well. So I'm going to go ahead and give you these numbers after the calculations have been made, and I ask you to find for me a 99% confidence interval for the average load capacity for beams made using this procedure. Also, is your target load capacity of 10,000 pounds, is it in this 99% confidence interval? So this 99% confidence interval is an estimation of the actual average load capacity. Is your target load capacity of 10,000 pounds in that interval? So pause the video and give that some thought. Alright, let's have a look at the solution here. So we know that our population is normal, and that means that the variance is finite. Normal random variables have finite variance. It's unknown, but it's known to be finite. It's also true that our sample size is greater than 40 here. So we are allowed to use the theorem which gives us the confidence intervals for populations with finite variance when the variance is unknown. So because our sample size is greater than 40, we don't actually need to know the population variance. We can use, or rather the population standard deviation, we can use sample standard deviation as a stand-in. So my 99% confidence interval, you'll remember, and you can remind yourself by looking at the last lecture, part 1 if you need to, that the z-value associated with a 99% confidence interval is 2.58. So we're going to have the sample mean minus our 2.58, sample standard deviation divided by the square root of the sample size, which is 101. So the sample mean that was observed was our 9,874. Our sample variance was 10,712, so we take the square root of that to get sample standard deviation. And we compute these values and get this 99% confidence interval for average load capacity of these beams. And our target load capacity of 10,000 pounds is not in this interval. So according to this estimation of average load capacity, we are underperforming where we wanted to be. Our average load capacity is falling short of the target by a considerable amount here, by 1% actually, even at the best estimate. So at this point, it might be appropriate to actually formulate a statistical test of the hypothesis that our average load capacity is 10,000 pounds. That's what we hope to be true, and based on a sample, we can decide whether or not we believe it's true or whether or not we would reject that hypothesis in favor of the alternative hypothesis that we're actually falling short here on average. And that is our next topic. So we are going to wrap up, this is going to wrap up our discussion of confidence intervals, and in the second part of today's lecture, we're going to begin thinking about statistical tests of hypotheses. This is the main portion of this is what we're going to do for the rest of the course, I should say. Statistical tests of hypotheses is an important topic. It's really it's sort of closer to the nuts and bolts of what working statisticians and even engineers who make good use of statistics, or people who work in a field like education who want to measure the efficacy of different educational approaches, working scientists, anybody who uses statistics on a daily basis. Statistical tests of hypotheses, it is bread and butter. It is the core of what is often done there. So we're going to spend the rest of the course, another good 3.5 lectures or so, discussing statistical tests of hypotheses. So thank you, folks. We will speak again in a moment.